So the setup for this problem is that we have a push button switch on RB13 with the weak pull-up enabled. So in main, we're going to configure RB13 as a digital input. We'll enable the weak pull-up on RB13. We'll enable the individual change notification interrupt on pin RB13. We're then going to clear the change notification interrupt flag. We will set the change notification interrupt priority to 2, and we'll set the interrupt enable for the change notification interrupt to a 1. At this point, the change notification interrupt is enabled, and then we're going to enter an infinite while loop, simply waiting for this interrupt, this ISR, to be executed. What is this ISR going to do? Well, the first thing it's going to do is going to disable the change notification interrupt on pin RB13, and then it's going to clear the change notification interrupt flag. Then it will exit. So the question for problem number 9 says, how many times did the change notification ISR interrupt execute for a single press and release of the switch? Well, initially, the input is high. When we press, we're going to get a high to low transition. That's going to cause a change notification interrupt, and so the ISR will execute. Once the ISR executes, we're going to disable this interrupt, clear the flag, and exit. That means that any subsequent changes on this pin, such as a low to high transition when the push button is released, will not generate a change notification interrupt. So the answer is that it will execute only one time on the falling edge of the input when the button is pressed. Problem 11 takes the code of problem 9 and changes statement D such that the change notification interrupt priority is now 0. The question remains the same. How many times did the change notification ISR execute for a single press and release of the switch? Recall the following conditions in order for the ISR to execute. First of all, the individual pin interrupt must be set to a 1. That must be enabled. We then need to have a change in state on the pin. The interrupt priority must be greater than 0, and the change notification interrupt bit must be equal to 1. So here what we have done is we have disabled the change notification interrupt ISR from executing by setting this change notification interrupt priority to 0. So the answer is 0. The change notification interrupt is not enabled, so the ISR will not execute. We would like to point out that because the individual pin interrupt is enabled, then this flag will get set on a change of state of this pin, except the ISR will not execute. The setup for problem 13 is that there's a single push button switch connected to two PIC24 inputs that are configured for int0 and int1 inputs with the weak pull-up enabled. This code here is going to do the following. We're first going to configure these inputs. Then this is going to configure the int0 interrupt. It's going to clear the interrupt flag. It's going to set the int0 interrupt priority to 2. It's going to set the edge polarity to 1, which is going to mean a falling edge triggered. And it's going to enable this interrupt. While this is the configuration code for int1 interrupt, it will clear the flag, set the priority to 2. Also set a falling edge for this int1 and enable the interrupt before going into an infinite loop. And the question is, give the order in which the statements A, B, C, D are executed for a single press and release of this switch. So statements A and B are in the ISR for int0, and C and D are in the ISR for int1. All these statements do the same. They're going to disable the interrupt by setting the interrupt enable bit to a 0, and then they're going to clear their respective flag. So let's see what happens on a single press and release of the switch. So on the press of the switch, you're going to generate a falling edge. Both of these interrupts, the edge polarity is 1, so both of them are configured for falling edge. They both have an interrupt priority of 2, and they are both enabled. So this is going to be the case of a simultaneous interrupt. So which of these ISRs are executed? It turns out that int0 has a higher natural priority than int1. What does that mean? If we take a look at the vector table, int0 comes before int1 in the vector table, so that means that this ISR will be executed before this ISR in the case of a simultaneous interrupt. So the answer is that statement A and B will be executed first. Once this ISR is exited, then statements C and D will be executed. So the statements are executed in this order: A, B, C, D. Problem 15 takes the same code of problem 13 and replaces statement G with this statement right here, which sets the edge polarity of int 0 to a 0, which means that this one is configured for a rising edge interrupt, while int 1 is still configured for a falling edge interrupt. So what order these statements are executed whenever we press and release the switch? Well, when we press the switch, we're going to generate a falling edge interrupt, which means that the int1 ISR is going to be executed first. So statements C and D will be executed. When we release the switch, we'll generate a rising edge interrupt, which means that int 0 will then be executed. So A and B will then be executed. So the answer is C, D, A, B. Problem 17 takes the code of problem 13 and modifies statement L such that int1 interrupt enable is now a 0. By the way, there's a book errata. The problem in the book says statement H when it should be actually be statement L. So now the question is, what is the order in which these statements are executed for a single press and release of the push button? Well, when we set interrupt 1 I equal to 0, we have now disabled the int1 interrupt, which means that only int 0 will be enabled, and so statements A and B will be executed whenever we get a falling edge on that interrupt, while int1 ISR, since it's been disabled, that ISR will not be executed. Problem 19 takes the code of problem 13 and deletes statement D and changes statement C such that int1 IE interrupt enable is equal to a 1. So now what happens whenever we have a press and release of the switch? Well, interrupt 0 is still enabled and it has a priority of 2. Int 1 is still enabled, has a priority of 2. So because int 0 has a higher natural priority and is configured for a negative edge trigger, it will get executed first. So A and B will get executed. Then this ISR int 1 will be executed after int 0 ISR exits. Because the interrupt is enabled and we've deleted the clearing of this flag, what's going to happen is once statement C is executed and we exit, we're going to jump right back into it. The interrupt is still enabled, we've not cleared a flag, and it's going to get hung up in an infinite loop, always executing this ISR. So the answer is statement A, B, and then C, C, C as we get stuck in the infinite loop. Problem 21 asks, how many PIC24 timer 2 ticks are equal to 1.2 milliseconds, assuming a prescale of 8 and an instruction cycle frequency of 30 megahertz? We know that in general, for a counter or a timer, time is equal to timer ticks times timer period. We know timer period, we're going to know time, we don't know timer ticks. So solving for timer ticks, we have time divided by timer period. For timer 2 on the PIC24, the timer period is 1 over the instruction cycle clock frequency times the prescale. So plugging in our numbers of time is equal to 1.2 milliseconds, our instruction cycle frequency is 30 megahertz, prescale value of 8, and solving, we get timer ticks is equal to 4,500. If we wanted to generate a periodic timer interrupt using these settings, then we would need to load PR2 with one less than this value, which would be 4,499. But this is a number of ticks, 4,500, corresponding to these values. Problem 23 asks, what is the maximum PIC24 timer 2 timeout period, assuming a prescale of 8 and an instruction cycle frequency of 10 megahertz? Give the answer rounded to the nearest milliseconds. So we know that time is equal to timer ticks times timer period. So how many ticks is a timer timeout? Well, a PIC24 timer 2 is 16 bits, so the number of ticks is 2 to the 16th, or 65,536, times the timer period of 1 divided by the instruction cycle frequency times the prescale. Multiplying these numbers out, we get this value in seconds. We need to convert this to milliseconds, so we multiply that by 1,000 milliseconds in 1 second. We end up getting an answer of 52.4 milliseconds, so rounded to the nearest milliseconds is going to be 52 milliseconds.